Today I thought we'd do something fun. I don't always just sit in front of my computer and write an app. That'd be crazy. All work and no play makes Bill a dull boy. Recently I started dabbling in training LoRAs in Quinn image and WAN 2.2 video generation using Ostris AI Toolkit. And you're looking at it right now. And I remember when I first started using this tool, I had no idea what any of those configurations and buttons and toggles, like what they would do. And I thought that we'd use today for me to go through each and every single one of them. I'm going to explain to you what they are, what they do, and the values I like to set myself, and just have some fun. You never asked for this, and I am here to deliver. Let's start. So I'm not going to explain how to install and get it running. There's a lot of tutorials online that you can look up, including the tutorials from Ostris AI Toolkit, the creator himself. By the way, he's amazing. Like, this is a one-person project, and he managed to make something that millions of people use. Maybe one day I'll be like him. Anyways, if we're looking at the very first section, the job section, training name, very straightforward. That's just a name that you assign the job. It doesn't really do anything other than telling you how to identify the job. So put in whatever you want, make it descriptive. GPU ID, this is the GPU that you will assign this training job to. And I have two GPUs here, and then you'll see more if you have more, you'll see fewer if you have fewer. The key thing to remember is that right now, and probably for the foreseeable future, it's unlikely that we'll be able to train on multiple GPUs at the same time. In other words, as far as I'm aware, AI Toolkit can only train on one GPU. So pick whichever one that you want to train the thing on. And one pro tip is that AI Toolkit does allow you to pause the training job and resume later. So conceivably, what you could do is if you anticipate different GPUs having different loads at different times, you could pause and switch GPUs, and that wouldn't actually impact negatively your training progress. Trigger word, and you can click on the question mark to read the verbiage here. Basically, the way to think about trigger word is when you are training a LoRA, and that's what you're doing right now, you're training a LoRA. You're not training the entire base model. You don't have the resources to do that. You're training a concept encapsulated in a low rank adaptation right here. It's a smaller file. And in order for the file to be used or reflected during inference in your workflow, not only would the LoRA have to be loaded into VRAM on top of the base model, you'd have to trigger it. And the trigger word is the word that you assign during training such that the LoRA knows when to wake up when the trigger word is uttered. And one key thing about the trigger word is that you have to use a trigger word that's not a very common word. In other words, you don't want to use the trigger word that's already in the base model, for instance. If you did that, then using the same word with the LoRA applied during inference, the model is going to be like, are you asking me for this particular LoRa's concept, or are you asking me for what's already encoded in the base model? It's going to get confused. So use a unique trigger word, and remember that this is the word that you'll use during inference to wake up and apply the LoRA that you have trained. That's the job section. Let's move on to the model section. Model architecture, there is actually a whole list of models available here. I'm going to talk about Quinn image here. For the most part, they are all very similar, if not identical. Their major exception, as far as I know, is the WAN 2.2 14 billion models, including the image to video as well as the text to video models, because these are mixture of experts models that warrant some additional consideration. I'm not going to address those things in this video. I might make another video talking about them because they might take a little more time than just Quinn image. But for the most part, if you're doing stable diffusion, if you're doing flux and Quinn image, you're going to be looking at roughly the same sort of setup right here. Okay, name or path. This is the path for the base model file that AI Toolkit is going to look at. If you already have the file downloaded, you can just point to it using this particular field, put in the file path. If it's not downloaded and AI Toolkit cannot detect it, it's going to actually automatically pull it from Hugging Face. And in that case, this field just becomes the path for the model on Hugging Face repository. Options. Low VRAM. You almost always have this option turned on. What this option does is that typically, if you have it turned off, typically if you have a large and powerful enough GPU to increase training performance, you would want to keep everything in RAM. And the problem with that is, of course, we don't have that amount of RAM. We want to offload things that don't need to be computed by the GPU at that time away from VRAM. Move it away from VRAM such that the VRAM can be used exclusively for what needs to be computed at that time. So if you have this toggled on, it's not going to magically make a model that's otherwise untrainable on a lower VRAM capacity on a lower VRAM GPU. However, it does allow you to offload VRAM intensive tasks that don't need to be in the VRAM at that particular moment. And this might be confusing, but as I explained the options, for instance, unload TE as well as cache text embeddings, you're going to get a sense of how this works. All right, let's move on to the quantization section. Transformer. So when you train a LoRA, you're training potentially two components. Now, the two components are the transformer as well as the text encoder. However, to be clear, in AI Toolkit, in almost all cases, you'd be training only the transformer. I've not seen a use case for, I mean, there is a reason to train a text encoder, but I have not seen a use case for training the text encoder in a sort of the amateur community. What this means is that despite the fact that you're not training a text encoder, in the LoRA, there's still the transformer and the text encoder because the text encoder will include information from, for instance, the captions of your training dataset or the trigger word. And what you're looking at the quantization is how much compression we apply to both the transformer and the text encoder. Because we're not training the text encoder, like, there's no reason not to use float 8. Float 8 is the highest quality quantization available for both the transformer and the text encoder. Because we're not training the text encoder, we don't really have any VRAM considerations. So pick float 8, no reason to go any other value. However, with the transformer, because we're training the transformer needs to be able to fit into the VRAM. So ideally, of course, you would want to use float 8 because, again, that's the highest quality. But if your training can't fit on your available VRAM, even after you turned on low VRAM, one option to reduce VRAM footprint is by reducing the quantization for the transformer. And anything lower than 6-bit, the community agrees that considerable performance degradation in terms of the quality output during inference is going to start taking place. And once you get below 4-bit, it's going to be just don't do it. Now, you might ask, what do I do if I don't have enough VRAM? One option here is using this 3-bit with ARA, accuracy recovery adapters. This is a specialty LoRa that's been trained by the creator of Ostris AI Toolkit based on a paper where the precision lost during training using 3-bit can be recovered, partially, with this adapter. And it's been incredibly effective, at least from my experience. It doesn't recover the whole thing. Like 3-bit with ARA is never going to be as good as float 8, but it's good enough such that if you can't fit anything above 6-bit in your VRAM, 3-bit with ARA is your best bet. And if you can't even fit that, we should start considering reducing VRAM footprint and some other configurations that we'll talk about in just a second. But 3-bit with ARA is as low as you want to go, other than 6-bit with the regular without the ARA adapter. Okay, we'll move on to target. The target type is almost always LoRA, because LoRA is just the target type that has the best compatibility with your tooling. If you're using LoRA in some weird tools here and there, like LoRA is always going to work. The other option here is Loker. This is a newer extension to LoRA. The way to think about this is to say a more efficient target type that might produce slightly better output, but it's not significant enough to warrant the reduction in compatibility with Loker. I personally have never used it. However, I do believe the latest version of Comfy UI does support Loker. So, give it a try if you want to. I personally have not had any experience with Loker. And with LoRA, everything works. So, I'm not going to fix what ain't broken. Linear rank. So as we mentioned earlier, when you're training a LoRA, you're not training the whole base model. You're training a low rank adaptation, an adapter to the base model. And the linear rank is the number of ranks, or the way to think about this is sort of how complex the adapter is. The higher the rank, the more complex, the more nuanced, the more information the low rank adaptation neural network can capture. So, the question is, well, we want to capture a lot of information as much as possible, right? So, get as high of a rank as we want. Well, that's not always the case. There are a couple of considerations to give. Number one, the biggest issue is that the higher the rank, as you would imagine, the more VRAM it would take. And we don't have enough VRAM. None of us has enough VRAM. So if we're running into VRAM constraints, reducing linear rank is one of the very effective ways to make the training fit on your GPU. And the other consideration is actually a very real one, which is if you keep increasing linear rank, the adapter becomes more and more. The way I like to think about this is less and less of an adapter, more and more of a base model. As the complexity of LoRA increases, there is the real risk of overfitting. When you're training a model, if you run into the issue of overfitting, the model sort of forgets its roots. It forgets how to generate anything other than what's been trained in the LoRA. That's undesirable. As one example, if you want to train a character, somebody that you want to be able to generate that person in different situations. However, your data set comes from, I don't know, the same set of pictures that you've taken in studio, right? And if the model's overfit, what could happen if you have a very high linear rank, it captured everything about this person plus the background, the lens characteristics, the distortion, the color palette, and everything else that's not this person. So during inference, when you're trying to come up with a new image of this person, it's going to look almost exactly the same as the set of images that you fed the LoRA during training. That's overfitting. We don't want that. And if you have very high linear rank, this is much more likely to happen. So the community wisdom around linear rank, defaulting to 32 is a good default for character LoRAs. The creator of Ostris AI-Toolkit has suggested that perhaps 16 is also a good number to use for if you're training with QuinImage specifically. Reason being that QuinImage is a 20 billion parameter base model. It's a gigantic image base model, and we don't really need as many ranks in LoRA to capture the characteristics of a character, for instance. And the general guideline is 16 perhaps for QuinImage, 32 for everything else. For character LoRA seems to be the way to go. Okay, next section, the save section. This section, I think, is fairly straightforward. Data type, there's really no reason not to use BrainFloat 16. Floating point 16 is not as precise as BrainFloat 16, and floating point 32 is literally twice the size. Why bother? Use BrainFloat 16. That's good. Save every. So during training, you're training it by steps, right? So down here we see there are 3,000 steps defined here. And save every, right here by default, every 250 steps, it would save a checkpoint. And then it would keep, by default, 4 copies of the latest checkpoints. And keep in mind that those LoRA files can be pretty big. If you use the linear rank 32, I believe every LoRA can be anywhere between 200 to 500 megabytes. So if you're leaving this training session overnight or over the weekend and come back, and if you don't like set those numbers to prevent a disk leak situation, your computer might lock up because your disk is filled. So, adjust those values based on your storage needs and storage capacity. All right, let's move on to the meat and potatoes, the training section. First one, batch size. This is, unless you have an NVIDIA H100, B200, or are really rich, it's almost certain that you will want to use the batch size of 1. During training, what you can do is you can look at NVIDIA SMI, or just if you're running in Windows, you can look at the Windows Task Manager to see how much VRAM you're using during training. If you find yourself having a lot of VRAM left over, you can bump up the batch size to increase the efficiency of training. What batch size does is that, let's say that we have a batch size of 2 right here, which my GPU can't do. If I have a batch size of 2, every step, the optimizer, which is, we'll get to that in a second, the optimizer, which is the engine of the training, would show 2 images to compute the weights, the updated weights for the model at any given time. So the idea being that not only do you speed up the training size, but you also potentially create better training results by showing multiple images to the optimizer and updating the weights at any given time. However, because of the VRAM limitations we discussed, most certainly you're going to keep it at 1. Now, the question being that how do we simulate the desired quality effect of using a larger batch size, but without the capability of fitting multiple batches in the same run? That's where gradient accumulation comes in. So if you don't have enough VRAM, but you still want to achieve the same quality as if you're showing the optimizer multiple images at any given step, you can set the value here. So setting gradient accumulation to number 2 is the same as setting batch size 2, but with gradient accumulation 1 in terms of the quality of the outcome. The only difference is that gradient accumulation, because you can't batch it, is going to significantly increase your training time. And the community is sort of divided on this value. The creator of Ostris AI-Toolkit, I've never seen him change this value. However, some other people have suggested that increasing it to 2 or 4, would increase the quality outcome a bit better. I personally have settled on the number 4. I seem to get better results more consistently if I were to use a gradient accumulation of 4. Okay, next is steps. That's just the number of steps, the number of times the LoRA weights are updated during training. 3,000 is I suppose, a conservative place to start. The way I like to use this is I like to set these steps to a very high number. So for instance, I set it to 10,000. Now I might not use all those 10,000 steps. However, I'm going to make sure, because I have a lot of disk space, I'm going to keep all the checkpoints. So in my train over a weekend, I come back and check the progress and see, oh, do I prefer the 7,500 step checkpoint better than the 6,000 step checkpoint? So that gives me option. However, if you want to reduce it and shorten it because you don't have enough GPU time, for instance, when you're using run pod, that's an option here. So 3,000 is a good place to start. I've seen convergence. In other words, I've seen a model becoming good enough past anywhere past 2,000, but it can extend depending on your data set, depending on all the other parameters that we have talked about, and we will talk about. So I like to keep it a higher number. Next, optimizer. The optimizer is just the engine of training. Its role is literally computing the numbers and then updating the weights of the LoRA that you're training. And there are two options here: Atom W8-bit and Eta factor. In almost all cases, we'd be using Atom W8-bit. It just works better. Eta factor is one that's used in training very large models, which is not the case here. If you're watching this video, you're not training a large model. Eta factor can provide some noticeable speed boost in those situations, but it's a bit more finicky, and it requires quite a bit more tuning. It's not as forgiving. So I have not seen anybody use anything other than Atom W8-bit, but just understand that optimizer is just the engine of the training, and Atom W8-bit is state of the art, is the one that you should use. Learning rate. This is the factor that's applied to how quickly weights are being modified during every step. It is the learning rate. The higher the rate, the more quickly a model, quote, learns. Then the question comes up, like, why don't we set it to 10,000, as quickly as possible? So as I explained before, this is a factor, a static factor, right? So if you can imagine this, if you apply a learning rate that's too high, sure, it might trend towards the desired weight more quickly. However, when it gets close to it, because the learning rate is a constant factor and it's too big, you can easily imagine it overshooting in one step and undershooting in another. In other words, it struggles to achieve convergence. So a high learning rate has this risk, and the community wisdom seems to be centering around, this is a good starting point, 1e-4, and the creator of Ostris AI Toolkit has suggested 2e-4 might be another good place to start to speed it up a bit. I think anything above 4e-4, you'd be playing with fire, but play around with this number and see, the level of endurance you have during training. I mean, you can leave it as is, a small number. It just would take more steps to get to it. But if you're in a pinch, increase it and monitor the outcome, and especially monitor the loss function, and make sure that it's not bouncing around. Next, weight decay. Weight decay is a regularization technique that's used to suppress the outsized influence of heavyweights. Okay, that's a lot of gobbledygook. The way I like to think about this is, when, let's say, you're training a LoRA, you're training a style LoRA of a particular, you want the pictures to take on a particular style. And there's certain essences in the LoRA that's being trained, being captured by the training process. And there are certain things that are essences that are very strong, resulting in very heavy weights in the outcome of the LoRA file. Now, problem with those heavy weights, well, the good thing about those heavy weights is that they capture the essence that you want to capture with the training process. That's the whole point. The problem with that is, of course, they might, again, overfit the model. If the heavyweights are there, not only would your entire picture during inference be following the particular style in the LoRA that you're training, it might influence for instance, the subject matter that you were not training, the background that you were not training, because again, the model is overfitting, and there's some heavy weights there that skew in the results towards overfitting. Weight decay applies a penalty to those heavy weights every time when the steps are run, as to sort of reduce the impact of those strong concepts such that your trained LoRa stays flexible and light on its feet during inference. However, I have never changed this number, and I don't remember seeing another community post about changing this number. So I would leave it at 1e-4 unless you're running into very specific diagnosable overfitting issues, in which case play around with this number and see what you get. Next one, time step type. Well, we should talk about time step type and time step bias together. But before we talk about those, let me briefly mention the diffusion model inference and training, sort of the outline of it. The whole point of diffusion is removing noise. If you tried diffusion inference in either Comfy UI or Automatic 1111, you notice that at the beginning it's all a jumble of noise, and then over time the picture sort of clears itself up, right? That's the noise removal process. And you can imagine at the very beginning, there's a lot of noise. We call that time period high noise. Let's say if you're generating Quinn image using 30 steps, the first 10 steps might be considered high noise. You can't really make out what's going on. The picture is just taking its shape, trying to figure out the composition, the character position, the background, and all of that, and the style and all of that. In the middle 10 steps would be considered, well, medium noise level, because you're in the medium. That's where, for instance, the person's outfit is being refined, the person's face shape, head shape are being refined, and stuff like that. And then the last 10 steps would be considered, well, low noise, because at that point, if you look at the picture, you can already make out most of the situation. You might even be able to tell who the person is. But the last 10 steps are spent on, for instance, refining the person's hair texture, the skin texture, the background bokeh, and stuff like that. So that's the whole diffusion process during inference. And it's the same situation during training. So, which means that depending on what you're trying to train, you would want to spend more time during a particular noise phase than any other noise phases. To give you one example, let's say I want to train a character LoRA. In other words, I want to train a LoRA, for instance, my wife. Right? I want to be able to use that character LoRA and plug it into a Quinn image and then say, okay, I want her to be drinking coffee. If you think about the way character LoRAs work, we don't really want to train character LoRAs on composition. Right? We want the composition to already mostly be done before our character LoRA information is sort of injected into the diffusion process. So in other words, we don't really want the training to be skewed towards the beginning, the high noise time, the high noise period when, again, the composition is being put in place. We would mostly want it to be in the middle, where the person's face shape, the hairstyle, maybe if you train the outfit and whatnot to be sort of determined during the medium uh, diffusion process, the medium noise period. And that's where the time step type and the time step bias would come in. Excuse me, that took a lot longer than I thought it would, but I think it's important to at least have this background before we look at the options. Time step type, there are 4 options here. I'm only going to talk about sigmoid and linear, and I'll explain to you why. So sigmoid is more like it's not exactly, but the best way to think about this is it's a normal distribution. It skews towards the middle. It skews towards what we want for a character LoRA training. In other words, almost certainly you would pick sigmoid for character LoRA because it would focus mostly in the middle, the medium noise period, where the training data set would have the biggest impact in terms of the character. Linear is even throughout. In other words, all 3 periods would get the same amount of attention. This is helpful, not necessarily in character LoRA training, but in the sort of a specialty case where, well, unfortunately, I won't discuss here. When you're using WAN 2.2, the mixture of experts model training, linear actually comes in pretty handy over there. And it's not exactly the most ideal way to do it, but perhaps I'll save it for another video explaining how linear interacts with WAN 2.2 text to video, the 14 billion mixture of experts model. Shift and weighted, as you can see from the names, shift and weighted mean that the time step would focus, the time step focus shifts to a particular, like it could be shifted forward, it could shift it backward. The problem is, and same with weighted, right? The weighted can mean it's weighted first half, second half, or first third, second third, or third, or first quarter. You know, any number of ways of shifting and weighting. Problem is, I have not been able to find documentation on these, so I don't know what they mean. If anybody knows what they mean, feel free to let me know down in the comments. And that's why I never actually used shift or weighted. So I would stick to sigmoid for character LoRA, linear perhaps for style LoRA and stuff like that. Time step bias is another refinement that we can do. Balanced is balanced. High noise skews towards the beginning, and low noise skews towards the end. And one key thing to keep in mind is that time step type and time step bias interact with each other. If you have a sigmoid and you say high noise, it's still going to look like a sigmoid normal distribution, but it's going to skew forward. And low noise, as a result, skews backwards. Right? That's the time step type and bias. Next one, noise scheduler. Noise scheduler is the algorithm that adds and subtracts noises from the latent space. But there we have two options here, flow match and DDPM. No reason to use DDPM anymore. DDPM is an older, more classic version, but everybody now uses flow match. It's got better performance, and it typically, well, almost always gives you better results. Okay. Next is exponential moving average. This one, a bit of a doozy. Typically, if you have this option off, when you're training, the weights are just being updated. That's it. Nothing else happens. If you turn this on, the training process will keep a copy of an entire copy of the trained weights, but using exponential moving average in resident memory. This typically results in smoother changes, again, because it's moving, it's using moving average. It's not just like straight up updating. In other words, every update, there will be a dampening effect applied by the moving average to ideally reduce or eliminate overfitting. Because as we talked about overfitting when we were talking about weight delay, the biggest problem with overfitting is strong signals punch through into the data set, into the trained model disproportionately. And if we apply a moving average, you can imagine instead of getting to the exact value, it would actually get to the moving average value after the new value is applied, which dampens and reduces the impact of strong signals. So if EMA almost always gives you a better result. And by the way, the EMA decay here is a number that you would use to signify how strongly, well, the EMA decays, right? The higher the number, the more strongly the dampening effect is with regards to applying EMA. Now, that said, I almost never use EMA. Why? Not because I don't want to, but because I can't. As you can imagine, EMA keeps a complete copy of the exponential moving average in resident memory, the entire model, in addition to another copy of the model. I don't have that VRAM. I doubt you do either. But if you do, and if you're really rich, turn this on, you're going to get better results. Next one, text encoder optimizations. This ties in with what we were talking about earlier with regards to low VRAM option here. Now, to back up a little bit, like I mentioned earlier, everything that we're training in AI-Toolkit, in Ostris AI-Toolkit, almost everything is just about the transformer, not about the text encoder. The text encoder, to be clear, the text encoder and the transformer will show up in the same LoRA file that eventually becomes the output of your training process. However, the text encoder is not trained. It's just the transformer. And as a result, and as you can imagine, if you have low VRAM, you can eject the text encoder from your resident VRAM such that you can fit a bigger transformer to train, bigger and better quality transformer to train. And these two options are interlocked with each other. Look how cool that is. Programming. Yeah. These are interlocked, and these offer the capability of ejecting text encoder. If you select unload text encoder, you can click on the question mark and you read the. By the way, this is not the first time I read this. I was like, what? I don't know what you mean. So I'm going to explain this for you. If you select the first one, unload text encoder, it's going to completely disregard the captions that you put in your data set. However, it will use the trigger word that you put here. So the trigger word would still work, but the captions would not. But you gain a benefit of ejecting the text encoder from VRAM. Now, what if you do want to use your captions? You would use cached text embeddings. That's it. That's the difference between those two. Now, there's a nuance here where, keep in mind, so if you're using cached text embeddings, because this is cached and not in your VRAM during training, you cannot use any dynamic text embeddings. And we'll talk about dynamic text embeddings down there when we're talking about data sets. But in most cases, we're not using dynamic text embeddings. So we can safely use cached text embeddings, put in your captions in your data set, as well as the trigger word, and you can be rest assured that these values would still be used in your output model, while at the same time saving you VRAM by caching it and not loading it into the VRAM during the training process. Regularization. That's a long word. Regularization is yet another technique to prevent model overfitting. So we talked about two techniques already. EMA is one option to prevent or at least reduce model overfitting. Weight decay is another. Now this is the third option. Differential output preservation. This is a even more, I suppose, sophisticated way of suppressing stronger signals. The way it works is during every step of the training, the optimizer would actually produce the inference output using the trained model and then compare the produced weights with the LoRA at that moment against the base model. And then, depending on the loss multiplier that you've set here, as well as the preservation class, apply a dampening effect on the overbright signals in the output of in the weights update in your LoRA. I don't know if that made any sense. To translate it into English, if let's say we are training for a character LoRA, you just want to train the characters, the likeness, the face. You don't really want to train, for instance, the apparel or even posture and stuff. If the model is overfit, the posture, the apparel, as well as perhaps even the background, the style of the photos, the lens characteristics would be captured by your model. However, with differential output preservation, you can specify this to be a person. And then what happens is, after every step, the optimizer is going to produce the weights during inference, using inference, and then compare the weights produced by, let's say, a person from the base model. And then they would compare and be like, oh, these weights are way too strong. We need to dampen it. We need to put a loss multiplier on it. This is the loss multiplier. 1 is a good place to start. If you want more loss, if you want to dampen more, you would increase this number. If you want to dampen less, you would decrease this number. However, as you can imagine, because it does multiple steps in one step, as well as being very VRAM intensive, this significantly increases your inference time. And training time. And I don't know if it's actually worth it. So I typically keep it turned off. That's the training section. Now let's move on to the last section. Datasets. This is a place where you specify the dataset that you want to include in training. You'd be training on a dataset, right? What else would be doing if you didn't have a dataset? Now, I'm not going to show you how to add a dataset. That's actually fairly straightforward. It's just be a bunch of pictures and captions. And there's plenty of tutorials on YouTube that can show you that. I'm going to talk a little bit about the options here. Dataset, that's the drop down where you can pick the dataset. I don't have any dataset right here, but if you had, you'd be picking one from here. LoRA weight, I I I don't really know why anybody would put a value of less than 1 or greater than 1. I just use 1 because, again, if you have concerns with regards to underfitting, you can tune a lot of those other parameters that we talked about. If you have concerns with regards to overfitting, you have multiple tools that can help you reduce overfitting without reducing the strength of the LoRa weight training. So I don't know why, but like I always use 1. So use 1 unless you have a compelling reason. Default caption is the caption that gets applied to your dataset if your dataset does not have captions. You don't have to put anything here, but I personally typically match my trigger word with default caption. Doesn't hurt. Also, I don't think it does anything. Caption dropout rate. Caption dropout rate almost certainly does not apply to you if you have low VRAM selected or cache text embeddings selected or unload TE selected. Because if you unloaded TE, you're not going to have captions. So your caption dropout rate would be 100%. If you have cache text embeddings selected, you're not going to have it's not going to do dynamic text embeddings. So it's just not, this value would be useless. Now, what is caption dropout rate? In training, again, to prevent overfitting, we sometimes choose to drop the caption and feed the optimizer just a picture without the caption. The goal is, of course, number one, to sort of strengthen the model to become more resilient, to not overly rely on your captions. And number two, because you're dropping out the captions, it necessarily reduces the strength of the signals that's punching through into updating the weights. So caption dropout rate is another dial that you can use to tune the training process to reduce overfitting. The problem, of course, I explained to you is that if you use any of the low VRAM options, you're not going to be able to use caption dropout rate. So just, ignore it or just use the default value. Settings, cache latents. Cache latents would cache the latent or latents of pictures. So as to avoid computation. Okay, what does this mean? When we in a data set we have pictures and captions, but before the pictures can be shown to the optimizer to update the weights, the pictures need to be converted to a different format, and that different format is called latent, a latent image of the original image. And that computation is expensive. If you have a very powerful GPU, that can probably be done very quickly. But if you don't, understand that every single step, the latent is recomputed for every picture. So if your GPU poor, GPU computational power poor, you can compute all the latents of all the pictures in one go and cache them on disk. Well, hopefully not on disk, hopefully in your memory. And then during every step, the optimizer, the trainer would actually fetch it from the memory as opposed to from it calculating it. So in other words, you're trading storage space for computational power savings. But and yeah, in that case, you might reap some minor benefits in terms of performance gain. I don't use it. I have a decent enough GPU, so I don't think I need this. But if you're GPU poor, if you notice that it produces better performance, yeah, use it. It's not going to change quality. It's just going to cache the latents at the beginning of training. Is regularization? It is essentially a toggle to designate your current data set as a regularization data set. We talked about regularization up here in training section, which is a way to teach the LoRA to not deviate from its roots too much. One of the techniques in a data set is you can feed a control data set, a data set that does not contain the concept or the character you want to train, to the trainer such that the trainer can understand, okay, this is not what we're trying to train, and other and if you and you need to designate it such that the optimizer knows that this is not the concept that you're trying to train, so that the optimizer can use it to make sure the trained LoRA output doesn't deviate, doesn't lose the ability to generate anything but the trained concepts. Now, obviously, if you use is regularization, it means that you have more than one data set, because the data set that you have marked as regularization data set is just not the concept that you're training on, right? Like if you don't have one data set and it's a regularization data set, it's a control data set, what are you training? So, again, if your trained model has a tendency of overfitting, this is another option, another tool in your tool belt that you can use to reduce the tendency of overfitting. I don't use it. It's way too much effort, bro. Like you'd have to come up with a whole new data set, caption them correctly, and then select this, and then increase training time, because again, those pictures have to be shown to the optimizer one by one as well. That's just too much effort, man. I got I got an app to develop, man. So I don't use it. You could use it if your model is overfitting. Flipping. Click on the question mark and read the help text at your leisure, but I'm going to explain it to you right here. If you can flip images on the x-axis or y-axis, from the computer's perspective, if an image is flipped, it's not the same image anymore. In other words, if you have a very small data set and you want to enrich your data set and increase the number of pictures in your data set, you can you can flip on the x-axis or the y-axis. However, you can already see the problem. Even if you flip the person on the x-axis, the person is not going to look exactly the same on the left side and on the right side. You might not notice, but if you flipped somebody's face, you're going to notice. Or if you mirror, have you ever done this? Like if you mirrored somebody's face using the center line and you realize that they look crazy as, I'm not going to curse in the video. You get the idea. That's just not going to work. So for landscape, perhaps you can use it. Anything without symmetry, you can use it. Anything where symmetry doesn't really matter, you can use it. You certainly don't want to flip y-axis on person or really on anything. Like, can you imagine a beautiful sunset scenery and it's upside down? That's not going to work. It's going to confuse the model. So almost nobody uses it. But in certain circumstances, these come in handy. So instead of, having to put in all the mirrored or flipped images in your data set, you can just, use those toggles. But almost nobody uses it. Resolutions. Okay, so the ones that are toggled on are the default resolutions that are specified by Ostris. And of course, the resolutions would have to, it's model dependent. If you're training on a model that's not capable of doing 1024, I mean, toggling this on isn't going to do too much for you. However, I believe Quinn Image native generation goes up to 1300, 13 something by 13 something. So it's pretty high resolution. And what these toggles do is that they create buckets for the training process. Let's say that you have a picture that's of resolution I'm making it up, of resolution 900 by 900. And if you have those toggles on, what would happen is at the beginning of training, that picture, because it's 900 by 900, is going to be downscaled to the next biggest bucket, which is 768. In which case your picture would become a 768 by 768 picture. And then that picture is going to be then converted to latent space and be pushed through for training. Again, because we're training over specific models, and models have preferences and tastes for different input resolutions. Now, obviously, the higher the resolution that your model architecture can support, the better the quality. But you're going to run into VRAM issues because, as you can imagine, the bigger the resolution, the bigger the resulting image is, and the bigger the latent space is, the bigger it will be in your VRAM. And if you can't fit in a VRAM, you just can't train. So use those. If you're running into VRAM issues, toggling it down and using lower resolution might be your saving grace. And fret not. Even if you're training at 768, for instance, at with QuinImage, at the end, you can still use the same LoRA to inference at a higher resolution. The only difference is, of course, the nuances that might be otherwise captured in a high resolution training data set might be lost. But the person is still going to, if you're training character LoRA, the person is still going to look, you know, like your person. It might just not capture the freckles or the imperfections of their skin, right? So it's not too big of a deal to go down, but if you have the VRAM space, crank it up, baby, crank it up. Okay, and that's it for dataset. Oh, dataset wasn't the last section, was it now? Now we're at the last section, sample. So the way that Ostria's AI Toolkit works is when you training takes forever. It takes a long time. Even on a very fast consumer GPU on any model worth their salt like QuinImage, you'd be looking at hours, if not days. So, and you don't really know at what point your model becomes good enough, or at which point your model overshoots and starts degrading, right? So you want to be able to monitor it, and sampling is the way that you monitor it. So this is the section that dictates the parameters for that. Sampling by default is 250. So every 250 steps, AI Toolkit is going to stop training, and it would go into an inference mode, and then it would generate using the sample prompts you have listed below. Now, what you're seeing here is a list of sample prompts by default coming from the software. But depending on what you're training and the trigger word that you're using, you might want to change those such that the concept that you're training or the character that you're training actually show up here in your sampling. And sampler use flow match. Like I said, DDPM. Nobody uses DDPM anymore. Guidance scale. This depends on the base model that you're using. I do not remember the guidance scale for QuinImage, but look up the documentation for your base model and use that value. Same for sampling steps. 25 is a nice conservative number. Width and height, the width and height for the images that you want to generate or sample during the sampling process. Seed is the seed 42. Nice number. I don't know how to explain seed. It's the starting point for latent noise. And if you have walk seed turned on, for every generation, it's going to walk the seed. It's not going to generate a brand new random seed. It's going to walk it. So for this prompt, it's going to use seed 42. For this prompt, it's going to use seed 43, 44, 45, so on and so forth. So it walks the seed. Why do that? Because it's deterministic. You can then compare and contrast if you want to reproduce those things. If you turn it off, everything's going to be 42. Easy peasy. Advanced sampling, skip first sample. When AI Toolkit starts training any model, it would typically perform sampling before it starts training. So the first set of pictures that come up would be your baseline. You can skip those to speed up sampling, but if you have time, don't skip. And force first sample does the exact opposite. Even if the first samples have been produced, you can force first sample if you've changed parameters down here or here. You want to redo the first samples. Have this turned on. Disable sampling, disables sampling. That's it. That's it. If you have any questions, number one, I hope this is helpful. It took a long time, and I definitely spent a good amount of time pontificating things that may or may not be directly related to this. But I hope you enjoy my explanations. And if you have any questions, feel free to leave them in the comments. I doubt that this video will be seen by many people. But if you do have questions, I love to hear from you. If you have any quick corrections, I'm sure I made many mistakes. Well, I hope I have not, but I have. If you notice them, let me know in the comments, and I'll update. I'm not going to be able to update the video, but I would be able to update perhaps the description or the pinned comment. And if there's enough interest, or if there's enough interest from me at night when I'm bored and don't want to work on my app anymore on that day, I can make another video talking about LAN 2.2, which does introduce some complexities that I think need to be addressed, that have not yet been fully addressed, I believe, by any YouTube video so far. Anyways, that's it. Thank you very much for listening to my soliloquy. I will talk to you later.